Welcome back everyone. So in today's video, we are going to cover some more problems from recent All India test series. So this is problem number 1. And in this question, we have two infinitely long current carrying wires who carry current I1 and I2. So the equations of the wires are given, and wire number 1 is basically a parabolic wire and wire number 2 is a straight line. We have to figure out the magnitude of force acting on one of the wires due to the other. Okay. So we have to find out their interaction force basically. Okay, so first of all, just by looking, the current in wire number 1 is in the positive y direction and the current in the parabola is in this particular sense. Directly by looking at the diagram, we can see that the force is going to be attractive, right? Because the currents are actually parallel, and whenever we have two current carrying wires whose currents are parallel, they actually attract each other. So now let's try to draw a better picture and analyze the forces acting on the wires. So the line current is carrying a current of I1 and the parabolic wire is carrying a current of I2. So now as we clearly know the magnetic field due to this infinite wire, we'll find out the force that the wire exerts on the parabola. Now let's take a current element on this parabolic wire, and let's say the length of this current element is dl. Now obviously guys, the magnetic field at this location due to the infinite wire depends on this radial distance, right? So let's say the radial distance from the wire, well, that is just going to be the x coordinate of the particle, because remember the line was in the y-axis, so this distance will simply be the x coordinate of this particular point. So the magnetic field acting on this dl element, it is going to be mu naught I1 divided by 2 pi x. Okay, so now whenever we have a current element and it is placed in an external magnetic field, the force acting on that current element is the current flowing through the wire, which is I2, times dl vector cross the magnetic field vector. Now guys, at the location of the dl element, the magnetic field is into the plane, right? So if you do dl vector cross b vector, the direction of the force vector turns out to be normal to the tangent at this particular point, right? And if you take a symmetrical current element down here at the same distance of x, here the df force will turn out to be in this direction. And as you can see, if you sum both of these components together, only the horizontal component survives, right? And the vertical component just cancels out. So basically our goal is to integrate the x cap component of the force. So for that, what we'll do is, let's say the angle with the horizontal is theta, so the angle df makes with the vertical is also theta. Right now guys, you can actually just use vector triple product and integrate it, or you can just simply take the component. So the force that we are interested in is the integral of df sine theta, right, which is the x component of the force, and the direction is in the minus I cap direction. So the magnitude of df is I dlb, right? So that will be I2 dl times the magnetic field, which is mu naught I1 divided by 2 pi x times sine theta. So now we have a lot of variables here, right? We have dl, theta and x. So the thing is, if I zoom in the dl triangle, this is the angle theta, right? So from here, dl sine theta is nothing but the change in y, which is basically dy, right? So this further simplifies as mu naught I1 I2 divided by 2 pi times integral of dy divided by x. So finally, this is the integral that we have to compute. Now we'll substitute x in terms of y, because we know the relation of how x varies with y for the parabola, right? The equation of trajectory is given in the problem. So from here, x turns out to be y minus 3 the whole squared, and there will be a plus 9, so there will be a plus 2 here, and they're divided by 8 here. So this is the variation of y with x, right? So now we'll just substitute it into our equation. So integral of this is similar to integral of 1 by a square plus x square. So this is a tan inverse integral, right? So this is nothing but 1 by the square root of this term, which is 4, times tan inverse of y minus 3 divided by 4. So the limits of y will be from minus infinity to plus infinity, right? So we'll set it from minus infinity to plus infinity. So tan inverse of infinity, or 1 by 0, is pi by 2, and minus tan inverse of minus infinity will be minus pi by 2. So this whole term just becomes pi. So we cancel out the pi with the pi and the 4 with the 4. The magnitude of the force comes out to be mu naught I1 I2, and this is the answer to the question, and the direction is in the minus I cap direction. So the answer to this question is beta equals 1. So now let's move on to the next question. Okay guys, so in this question we have a non-conducting ring whose mass m and radius is given. It has a charge density lambda, which is lambda naught sine theta, where lambda naught is a positive constant and it is placed in front of an infinitely large, uniformly charged non-conducting sheet whose charge density is given to be sigma. If the ring is in pure rolling motion, so it's rolling without slipping, then we have to figure out the acceleration of the center of mass of the ring, Okay guys, so this is the situation. So an infinitely large conducting sheet over here. So basically the field due to the sheet is going to be sigma by 2 epsilon naught towards the right everywhere on the ring, right? Now guys, it's given in the problem that the ring is in pure rolling motion. Okay, so we can say that the acceleration of the center of mass is, let's say, a, and the angular acceleration of the ring, let's say it is alpha. So we can relate both of them by using the no slip condition as a equals r alpha. Right, so we can also say that this point over here is the instantaneous center of rotation. So now let's say the friction force is acting towards the right. The normal force is obviously going to pass through the center. So, and the mg is also going to pass through the ICR. So if I am interested in the torque about the ICR, we only have to analyze the electric force for that matter, because the normal reaction, the friction force and the mg, all of them pass through the ICR, so their torques become 0. So now let's analyze the electric force. So now in the ring it was given that the charge density varies with the angle theta. So, and it was given as lambda equals lambda naught sine theta. So it's a sine function, so which means from theta equals 0 to 2 pi, which represents the upper half of the ring, everywhere the charge density is going to be positive, and for the lower half, similarly, everywhere the charge density is going to be negative. Okay, so now the thing is, on each dq charge, the force acting is going to be sigma by 2 epsilon naught times dq, because the electric field is constant, right? We only need to pay attention to the direction of the force, because on negative charges, it will be towards the left. So let's say I take a very tiny arc over here. Okay, so I'm talking about this particular charge over here. So the charge dq on this part is the charge density lambda naught sine theta times the length of that arc, which is going to be r times d theta. So this angle, I'm saying it is d theta. Okay, now guys, if I take a symmetrical element such that this angle is theta, or basically even this angle is pi minus theta, so the linear charge density at this point is going to be lambda naught sine of pi minus theta, which is the same as sine theta. So they are symmetric, which means even here the charge is going to be dq itself. Now similarly, if I talk about a small charge at an angle of minus theta, here the only difference is that charge is going to be same, but the magnitude is going to be minus dq, and exactly using the same argument, here also the charge is going to be minus dq. Now guys, the net electric force is 0, as you guys can see, but there will be a non-zero torque. Right, so let's say this is the instantaneous center of rotation. Now the force acting on this dq is in the horizontal direction, and it is equal to the electric field, which is sigma by 2 epsilon naught times dq. And now even for this dq, the force is the same, right? And for this dq, it will be df towards the left. Similarly, even for this dq, it will be df towards the left. Okay, so now I'm going to write down the net contribution to torque due to these 4 charges. If you observe something, guys, the net force due to these 4 dqs are 0. Right, which basically means this 2df and this 2df forms a couple. It forms a couple force, right? And the torque due to couple force, I can write it as the force multiplied by the distance between them. And this is true about any axis. Okay, so this is true for all couple forces, and the force is df plus df, which is 2df, right? So this is going to be 2 times df, which is sigma by 2 epsilon naught times dq, and the perpendicular distance between these two forces is this particular distance over here. And this distance, if you see, it is r sine theta plus r sine theta, which is 2r sine theta. So this is basically the torque due to these 4 charges that we took. So now as I want the total torque due to electric force, I'll just integrate this. Now guys, the limits of theta is pretty important here. So if I start from theta equals 0 to theta equals 90, then it will cover all of these charges, right? As we took a symmetrical charge on the left side, even all these charges will also be covered. So basically the entire ring will be covered if I go from theta equals 0 to theta equals 90. So our limits of theta will be from 0 to pi by 2. And the integral of sine square theta from 0 to pi by 2, it comes out to be pi by 4. Okay, so you can use the King's rule here. So once you integrate this, so this is the torque due to the electrical forces. Okay, now you guys can as an exercise try to find out the net torque about the center of mass. So there also you'll get the same value because of this particular fact over here. Torque due to couple forces doesn't depend on the choice of coordinate. So even if you choose ICR or CM or any particular point, the torque due to the couple will come out to be the same. So the direction is simply into the plane. Now this is the only torque about the instantaneous center of rotation. So we can say tau equals I about the ICR, which for a ring is 2mr squared times the angular acceleration alpha. Okay, so from and after solving, you'll get the angular acceleration as this particular value. So now as it is pure rolling, the acceleration is nothing but r alpha. So now in the options, now in the question they wanted us to figure out this value of x. So that, as you can see, comes out to be 2. Okay, so the answer to this question is going to be 2. So now let's move to the next question. So in this question, we have a non-metallic sphere which has a uniform surface charge density sigma. So a point P is given as shown in the figure A. So the nearest distance of point P from the surface is infinitesimally small. So it is first of all present inside the sphere and it is very close to the surface. So now the hemisphere is cut and struck to the other half as shown in the figure, as shown in figure 2. So if sticking has no effects on charge distribution, so the sigma remains, so the sigma of the hemisphere still remain the same, then we have to figure out the electric field at point P due to this new arrangement. Okay, so give this problem a good try, guys, and then check out the solution. Okay guys, so first and foremost, the point P was present inside the non-metallic sphere, right? So now this is quite straightforward. We can directly write the electric field at point P as 0. And this you can just prove by Gauss's law as well, right? Points inside the charged sphere, the electric field is 0, and outside it is kq by r squared. So now we have to observe some patterns here. So imagine this like a watermelon and I'm trying to bisect it into two pieces. So now guys, I'm calling the hemisphere on the left part as number 1 and the hemisphere on the right as number 2. As we know that at point P the electric field is 0, so by superposition theorem we can say that this is E1 plus E2. So E1 is basically the electric field due to hemisphere 1 at point P. Okay, and E2 is going to be the electric field due to hemisphere 2 at point P. So their vector sum has to be equal to 0. Only then at the point P the electric field is going to be 0. So from here we can see that the modulus of E1 is the same as the mod of E2. So they're both equal in magnitude. So this is an important result. So just to summarize the point a bit, if I take a hemisphere something like this, then the electric field due to this guy at this particular point P, if I take the hemisphere something like this, then the electric field due to this hemisphere at this particular point, these are both equal in magnitude. So that if I superimpose these two hemispheres, these two E's cancel out and give us a 0 field at the inside point. Okay, so in the original problem we have to find the field at this point due to this configuration. Okay, so let's say this is hemisphere number 3 and let's say this is hemisphere number 4. Now due to hemisphere number 3 at point P, we know the electric field, right? That is basically E. So this we can just directly write it as E. So now we only have to determine the electric field due to hemisphere 4. So let's just move point 3 for a second. Okay, so now let's just focus on this particular situation. So in this situation, as we can see, green point is an outside point to the hemisphere, right? So how do we figure this out? So for that, we'll take the help of hemisphere number 2. So let me draw a better picture of hemisphere number 2. So let's say this is hemisphere number 2, guys. The point P is over here. Okay, we know at point P, which is basically just inside, we took the electric field to be E towards the left, right? And observe this green dot. This is just outside the hemisphere. So in this situation, if I can find out the electric field at this green point, then my question is done. So let's say that electric field is just E prime. So for that, what I'm going to do is I'm going to take a pill-shaped Gaussian surface whose ends are just inside and just outside of the hemisphere. Okay, if I draw it on the sides here, inside the electric field is E and outside and on the right side the electric field is E dash, and let's say the area of cross section of the Gaussian surface is dA. So basically we can say that the total enclosed charge within the Gaussian surface is going to be sigma of the hemisphere times dA. So now we can use Gauss law for this Gaussian surface. So we can say the total outward flux is going to be E dash plus E into dA, and this will be equal to the net charge enclosed, which is sigma dA divided by epsilon naught. So from here we get the value of E dash as sigma by epsilon naught minus E. Okay, so finally we have figured out the electric field at this particular point. It is going to be sigma by epsilon naught minus E. Okay, and now let's bring back our hemisphere number 3. So due to hemisphere number 3, the electric field over here was E towards the left, and due to hemisphere number 4, it is going to be sigma by epsilon naught minus E towards the left. So the superposition of these two will give us the actual electric field at this particular point, and that, as you can see, the E's just cancel out and the answer just comes out to be sigma by epsilon naught. So that was the solution to this problem. So the answer to N will be just 3. Okay, so that was it for this video, guys. If you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.